Hello everyone, welcome to the European Non-Associative Algebra seminar. I'm glad to introduce the speaker of today, Omar León Sánchez from the University of Manchester. He's going to talk on a Poisson basis theorem for symmetric algebras. Please.
Right. All right. Well, first of all, thank you very much to the organizers of the non-associative algebra seminar. It's very nice to be given the opportunity to give a talk here. Right. So I want to talk about this work that I did with Susan Sierra. Now it's been a couple of years now. I will talk about how this work initiated and the sort of things that we did, the sort of things that we expect that might be true. I have to say that after we wrote the paper, right, I've been doing other things. So I haven't been actively working on this for the past year, but I think there are still some interesting questions around this. And of course, if there's any questions at any point, please do let me know. Just unmute your mic. Okay, so I'll just go ahead with this. Let me quickly oh yeah, good. I was able to minimize that window. Okay, now I think if I do this, okay, good. Okay, so I hope everyone can hear me, and I hope the slides are clear and visible. Yeah. Okay, so first of all, what are the goals for today's talk for the next nearly 50 minutes? So I'm going to try to state a basis theorem for a wide class of Poisson algebras. I will give definitions along the way. I will also state a suitable division algorithm or elimination result for this class of Poisson algebras. Okay. Now today the convention will be that I'm going to be working over a field K of characteristic 0. Okay, and some of the results that we have, we have to put the assumption that K is algebraically closed. Not all of them. No, actually, most of them, they don't need that, but some of them do. So if you like, we might as well assume K is an algebraically closed field of characteristic 0. Okay. Okay, quick reminder, what's a Poisson algebra? So a Poisson algebra over the field K is a commutative algebra which comes equipped with this additional structure, right? This bilinear map goes from A cross A to A and is skew-symmetric. In addition to skew symmetry, it satisfies the Jacobi identity, the usual Jacobi identity. And one of the most important part of the definition is that once you fix, well, you can fix one of the two inputs, it doesn't really matter, but okay, once you fix one of the inputs in this bilinear map, then that unary function, right, now it becomes, once you fix one of the entries, it becomes a unary function from A to A, and that becomes a derivation. In other words, satisfies the Leibniz rule. It satisfies the Leibniz rule that applied to a product xy, it splits as the calculus Leibniz rule. Okay. Good. So this is what a Poisson algebra is. Now, what I will be talking about is a special class of Poisson algebras that arise naturally from Lie algebras, right? So first of all, recall that a Lie algebra is a vector space with the additional structure of a Lie bracket, which is nothing else than a skew-symmetric bilinear map that satisfies Jacobi. Okay, so in a Lie algebra, you don't yet have a product, right? It's just a vector space, and you do have the Lie product, right? But you don't have this associative product. Okay, well, one way to construct a Poisson algebra from a given Lie algebra is by taking the symmetric algebra of G. Okay, so you take a Lie algebra, you pass to the symmetric algebra, and in the symmetric algebra, there is a natural canonical Poisson structure, Poisson algebra structure. And this can be very explicit. This can be done very explicit. Okay, how do you do it? You take your Lie algebra G, okay, it's a vector space over the field K. So you take a basis, we call it this capital M, okay? The symmetric algebra can be identified with the usual commutative polynomial ring in variables M, okay? And then, okay, so that's the underlying algebra. Now, what is the Poisson structure? Well, the Poisson bracket can be naturally and uniquely induced by imposing that it acts as a derivation once you fix each entry, and on basis element, it's the given Lie bracket. So in the last line there, you can see that the curly bracket denotes the Poisson bracket. Okay, so now I apply it to M1, M2, M3. Now I am imposing that it should be a derivation once I fix the first entry. So I just apply the usual Leibniz rule. Okay, and now in the next one, you can see that I have curly bracket M1, M2, but M1, M2 are basis elements. So that just becomes a square bracket. So the standard Lie bracket. Okay, so using the Leibniz rule, you can easily induce a Poisson structure in the symmetric algebra. Okay, so I hope that's clear. Start with the Lie algebra, and then pass to the symmetric algebra, and equip that with the canonical Poisson structure. Okay, good. I hope so far everything is clear. Do let me know otherwise, please. Okay. And now here's a general sort of philosophical question, if you like. If you give me a Lie algebra G, for which of those does the symmetric algebra have the ascending chain condition on what? On radical Poisson ideals. Okay? Yeah. So you're asking questions about certain specific Noetherianity of the symmetric algebra, but of course you need some information, right? You need some assumptions. So what are the assumptions on the underlying little g? All right. Well, okay. As I said, it's a general type question. Okay, and the first thing you observe is a little lemma saying that if the symmetric algebra with the canonical Poisson structure has ACC, the ascending chain condition, on radical Poisson ideals, then the little g had to be Lie Noetherian to start with, right? You have to have Noetherianity of Lie ideals in the underlying g. Okay, so that you have to have that. Okay, but certainly that's not going to be enough. It's not gonna be enough. Okay, and so you can start asking these sort of questions. You know, what sort of things do you need to guarantee some sort of, how to say this, some sort of transfer principle of Noetherianity from little g to some sort of Noetherianity to symmetric algebra of little g. Okay. Okay, and I just wanted to point out here that there are examples of Lie algebras that are finitely generated as the algebras that are not Lie Noetherian, right? So like the free Lie algebra in two generators. Okay, so definitely Lie algebras being finitely generated doesn't really give you much. Okay, so definitely being finitely generated as a Lie algebra is not enough to get ascending chain conditions on the symmetric algebra. Okay, and you can see in the last line that I'm asking you to sort of compare this to what is usually called the differential basis theorem. I will recall what that is in the next two slides, I think. Okay. Once you see the differential basis theorem, you will see the sort of drastic differences, but also will help us motivation. Okay. Okay. So far, I'm asking kind of general questions. When can you get ACCs on radical Poisson ideals for the symmetric algebra? Okay. Okay. So another kind of direction to, or another approach to motivate this is another general question, which is, for which the algebras is the enveloping algebra two-sided Noetherian, right? Again, this is a general question, right? And in a paper of Alexei Petukov and Susan Sierra, they studied this question in the setup where the Lie algebra is the positive Witt algebra. Okay. Well, just to remind you that the positive Witt algebra is the algebra that has bases positively indexed by ENs, and the Lie bracket is given by that formula, right? And one way to try to prove that the enveloping algebra is two-sided Noetherian would be to try to prove that the symmetric algebra of the positive Witt algebra has ACC on all Poisson ideals. Okay, if that were true, if it were true for all Poisson ideals, then it will follow for the two-sided Noetherianity of the enveloping algebra. Okay, but as far as I know, we don't know an answer to that. Maybe someone in the audience can correct me, but as far as I'm aware, we don't know that. But what Alexei and Susan proved in that paper was that you do have Noetherianity at the level of radical Poisson ideals. Okay, so once you add this radicality assumption, then you do get it. You do get ACC. But I think for the whole collection of Poisson ideas remains open. And if you look at that paper of Alexei and Susan, then you will see that the argument that they used to prove the ACC on radical Poisson ideas, it has a similar flavor. Of an argument, or of the standard argument for differential basis theorem. Okay. And this is, for me at least, this is where all this started about maybe 3 years ago. I was talking to Sue about the paper, about their paper with Alexei, and I don't know, and we started discussing the possibility of exploiting the argument of the differential basis theorem. Right? We said, okay, maybe the differential basis theorem argument can be translated or adapted to the Poisson setup. And then Sue asked me about the following. So they proved the ACC condition on radical Poisson ideals for the symmetric algebra of the positive Witt algebra, But back then, as far as I know, it wasn't known for the full Witt algebra. So instead of taking the positive Witt algebra, how about you take the full Witt algebra, right? And then you take the symmetric algebra, whether that has ACC on radical Poisson ideals. Okay, and as far as I know, that was open 3 years ago when I was talking to Sue. And the same question, if now you take the Cartan algebra W1, which is just the subalgebra of the full Witt algebra when you start at n minus 1. Okay, so the first Cartan algebra. Okay, and again, 3 years ago, as far as I know, this was not, it wasn't known what happens in the symmetric algebra of these two Lie algebras. Okay. Okay, so I hope so far everything is okay. Again, please do ask questions. And just allow me to shut the door quickly. Apologies for that. Right. Okay. Okay. Now, a quick reminder of what happens in a setup that I sort of come from this side. I come from differential algebra. I consider myself a differential algebraist, so this is what I feel most comfortable with. take a field equipped with finitely many commuting derivations. Okay, so remember, these are just additive maps that satisfy the usual Leibniz rule. Okay, so case of field, characteristic 0, equipped with commuting derivations. It is a well-known theorem that the ring of differential polynomials over K satisfies the ACC on radical differential ideals. Okay, this is standard result. Now, the proof of the differential basis theorem, it has several aspects, but I want to stress out two of them. There's two key aspects in the proof that play a role, and they are very sort of present in other Noetherianity arguments. Okay, so the first one is the fact that you can consider this vector space V. What is V? V is just the vector space that is spanned by applying the derivations, all of the derivations, to the variables. Okay, so I have x1, x2, x3, xn variables, and I apply all the possible deltas and compositions of deltas, right? And then I take the span over K. So this becomes a vector space, okay? And the key fact, right, is that this is a differential vector, it's actually differential vector space. It is also n-graded naturally by the order of delta, naturally n-graded, and is differentially Noetherian, right? Meaning that it has the ACC on differential subspaces. Okay, differential subspaces. Now the reason why is this true? Sorry, maybe I say this in the next slide. I don't quite remember. Oh yeah, that's right. So why is this differential Noetherian? Where does this Noetherianity at the differential level comes from? Well, it follows really almost immediately from the what is classically known as Dickson's lemma. Dickson's lemma. What is Dickson's lemma? Just to quickly remind you, Dickson's lemma says that if I take the grid of the lattice of natural numbers to some power, n to the m, right? So just the just n to the m, and I take now the product order. I take the product order in n to the m, right? Then there is no infinite sequence, right, of incomparable elements. There is no infinite sequence of incomparable elements. Okay, this is a standard classical result from combinatorics, and it gives you differential Noetherianity. Okay, so Dickson's lemma, this Dicksonian property, is the key behind this differential Noetherianity for this differential vector space. Okay, and the other thing is to note is that the differential polynomial ring, this is what I wrote here, differential polynomial ring is just the symmetric algebra of the vector space V that I wrote in the previous slide. Okay? Okay. I hope the analogy to the Poisson setup is more or less clear. Okay, so that was one aspect for the differential basis theorem. The second main ingredient is to develop an elimination algorithm. You want to develop an elimination algorithm. Okay, and this is again a standard that if you give me in the differential polynomial ring a prime differential ideal, then I can perform elimination algorithms and show that every differential prime ideal P has this shape. P is equal to the saturation of a finite subset. This lambda is finite, right? And this element H, which is not in P, right? So it's a saturated ideal given by a finite subset of P, and then an element not in P. Okay, so this is a second ingredient for the differential basis theorem. Is that okay? Okay so far? Please do let me know if I'm going a bit too fast or or if there is any notion that I should explain. No, I don't see. Yeah. Okay. Good. Okay. 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 So having that review of differential basis theorem, now I want to go back to Poisson, the Poisson setup. Okay. So in the Poisson setup, I'm gonna be working in a class of Poisson algebras. Okay, it's still quite interesting and still a wide class of Poisson algebras, which is the graded ones. Okay, so I'm gonna start by saying that remember that a Lie algebra is said to be graded if there is a decomposition of the Lie algebra, this form, satisfying that the bracket of two homogeneous components is the bracket of Gn with Gm is in Gn plus n. And I am going to assume that each of the homogeneous components is actually a finite dimensional vector space over K. Okay. In addition, I'm going to assume that this graded Lie algebra has polynomial growth. Okay. What this means is that if I look at how the dimension of each finite, the dimension of each component, which is finite dimensional, if I look at that, how it grows as I increase n, then it grows at most a power of n. Okay. So this from now on, this is going to be my assumptions for my underlying Lie algebra. It's a graded Lie algebra with finite dimensional homogeneous components and is of polynomial growth. Okay. Okay. And now remember how before the construction of the differential polynomial ring, it was given by the symmetric algebra of the differential monomials. Okay, and it was graded and it was also of polynomial growth. You can show that the vector space V in the differential context, it grows polynomially. So kind of having that knowledge from differential algebra, I think it's naturally to expect that in the Poisson setup, if you start, okay, this is just an expectation, okay, intuitively, that if you start with the Z-graded Lie algebra of polynomial growth, if the Lie algebra is Noetherian, then that Noetherianity should transfer to the symmetric algebra as Noetherianity for radical Poisson ideals. Okay, that's sort of the expectation. Okay, but as far as I know, again, this remains open. I don't know a proof of this. But what Sue and I did was, okay, start with a Lie algebra, which is graded of polynomial growth. And now we're going to ask something slightly stronger than Noetherianity. Okay? And that condition is what we call Dicksonianity. We introduced a notion for Lie algebras, which is when is a Lie algebra Dicksonian. Now, the reason that we call it Dicksonian is related to the Dickson lemma that I mentioned, right? Remember that what I said was that in the case of differential vector spaces, you do get differential Noetherianity from Dickson's lemma, from this combinatorial result called Dickson's lemma. And so here we just try to make sort of the adaptations of this Dickson lemma to the Lie algebra context in order to get a similar flavor result. Okay? So what I will spend most of the rest of the talk is about what is this Dicksonianity? What do I mean for a Lie algebra to be Dicksonian? And then after I explain, well, after I, not super formally, but I will try to give you an idea what does that mean. I will first of all observe that there are examples. There are examples, actually quite a lot of examples of Dicksonian Lie algebras. And second, that assumption of Dicksonianity is sufficient to get the ACC on radical Poisson ideals for the symmetric algebra. Okay, so again, we strengthened the assumption of linear-theoreticity for Dicksonianity, and then we actually get this conjecture or a version of this conjecture. Okay, hope that's clear. Again, any questions, please do let me know. Okay. Okay. So that what I mentioned in the last two slides, it was to address this Dicksonianity, this Dicksonianity. Now, for the differential basis theorem, there were two ingredients. One of them was Dicksonianity, Dickson's lemma, and the other one was an elimination algorithm, right? I mentioned this division algorithm, standard result. Okay, let's see an example. Let's see an example trying to move in the direction of a elimination algorithm for this class of Lie algebras. When I say this class, I mean graded of polynomial growth. Okay, so take the Witt algebra. Okay, the full Witt algebra. The full Witt algebra. Remember, this is algebra with basis En, with that Lie bracket, and now it has a natural grading. The grading is just given by, the direct sum of the Ens. It is actually it's polynomial growth because it actually has constant growth equal to 1, right? And now, in order to attempt, whenever you are trying to attempt an elimination algorithm, one of the first things you need to do is fix a ranking, right? If you remember, maybe year 1 or something, that when you talk about the standard one variable division algorithm, right? There's always this sort of you have a ranking in mind, right? You can compare polynomials in some sense. And then when you move on to year 2, well, I don't know when you do it, but you talk about the division algorithm in now several variables. You have several variables, X, Y, Z or something, and you want to come up with a suitable division algorithm. Well, you need to put a ranking on X, Y, Z, which one comes first, right? And then you move on to doing Grobner basis stuff. Then you definitely need to put a fixed ranking. So whenever you're trying to do elimination algorithms, you need to fix a ranking and then work, with that ranking. Now, in the case of the full Witt algebra, there's a natural ranking, a natural order, okay? So in the last paragraph says, note that we can put a total order on the basis EIs and EJs by simply saying, EI is less than EJ if and only if the index I is less than the index J. That's it, right? And for us, what it becomes very relevant is that this order is completely compatible with the grading. In this case, it's actually given by the grading, of course. But whatever order we put in our Lie algebra, we need to know that it is compatible with the grading. What do I mean? I mean, if you have one element being less than other in the grading, right, in the grading, then it implies that the same inequality holds for the order. Okay. Okay, so having given this the example of the full Witt algebra, now in general, if I take the graded Lie algebra, G, for this definition, you don't need polynomial growth, but as I said, let's just assume polynomial growth from now. Okay. And now, what I'm going to fix from now on is a basis. I want to fix a basis for the Lie algebra, and the elements in this basis, they are all homogeneous, okay? I don't want mixed terms. I want an element in M, let's say, I don't know, little m, it's homogeneous of a certain degree. And I'm going to put a total order on this basis, which is compatible with the given grading. Okay? And this is going to be the assumption from now on. I have a graded Lie algebra with such a ranking. I hope it's more or less clear. Again, keep in mind the bit algebra example. In the bit algebra example, the order or ranking is just the grading one, just the one given by the grading, okay? Yeah, so keep that in mind. Okay. Okay, now, as I said, the symmetric algebra can be identified with just the polynomial ring, okay? And it has the Poisson bracket, okay? And now, in order to develop a division algorithm, right? Usually things get technical when you try to, say, okay, what is the suitable division algorithm? You need to eliminate things, right? You need to reduce things. And those things get a little technical, so please bear with me. But I have to say that this is the natural thing to do, okay? This is if you're going to develop an elimination algorithm in this setup, this is what you have to do, okay? Okay, let's start. So take F to be a element of the symmetric algebra, okay? And again, think of the symmetric algebra, as the polynomial ring. The polynomial ring where the variables are the basis for the Lie algebra. So it is a polynomial ring, okay? Okay. Now, what's the upper leader? Okay, so I'm going to define the upper leader of F, okay, to be the largest element in my fixed basis that appears in F. Okay, so I have F. F lives in the symmetric algebra. Okay, so it can be written as a polynomial. It can be written as a polynomial in terms of the basis of the Lie algebra. So I look at that polynomial expression and I look at all the entries, I look at all the non-trivial entries in there, and I just try to find the one of maximal order, maximal rank. And that's the upper leader, right? The largest one. That's the upper leader. Okay. Again, if you've seen these elimination algorithms before, this should be making sense. Okay. If not, please bear with me, but this is really the natural way of doing it. Now, once you do this, okay, you fix this sort of leader. You fix this. You fix a leader, right? This is your largest element. You fix this leader, and then you think of that monomial. You think of that monomial, and then you write it as a polynomial expression. You write as a polynomial expression where your leader. You now think of the f as a polynomial in one variable, the leader, and the coefficients are the other variables. It's just the usual thing, right? You have a polynomial in several variables, you choose one of them, and then you think as a polynomial in that chosen variable, and the coefficients are the other variables, involve the other variables. Okay. Okay. Now, once you write it like this is uniquely expressible in this way, right? It's only a unique way to express it in this way. Okay. Then the leading term is called the upper initial. The GD, if you want, the GD, the leading term of this one variable polynomial is called the initial. And then if you take the formal derivative, by formal derivative, I just mean as the one from high school, the one from school, okay? You think of it as a polynomial in the one variable, and you take the derivative with respect to that single variable, and that's called the upper separand. So we have the upper leader, we have the upper initial, and we have the upper separand, given any little g. Is that okay? Any questions so far? No? Comments? No? Okay. And now, the reason I was using the prefix upper, right, is because our Lie algebra is Z graded, right? So it's not graded by the natural numbers, it's graded by the integers. So it has, like, if you give me an F, you're gonna find something of which is the largest thing, but you also be able to find the thing which is the smallest thing, right? And with respect to the order. right? So you want to find the largest thing. And remember, these are always finite terms, right? Because it's a polynomial. So polynomials are always finite sums. So it has a largest element and a smallest element. So you can repeat the same notions, but now you take the lower leader, the lower initial, and the lower separand. And everything is now with respect to the smallest element from the basis appearing in F. So maybe it's good to see an example. Okay. So again, take the Vita algebra. Take the Vita algebra again. Remember, the basis is given by ENs. Okay, and just choose a random element. I literally just chose a random element. So it's e minus 2 squared plus e minus 1 times e naught plus e2 times e5 cubed, right? Well, you look at this, and then if I ask you to say, okay, which one is the largest element in the basis appearing in F? Well, you look at it for a second and you tell me, well, it's E5, right? E5 is the largest element. Now, once you think of this polynomial in that variable, so in the E5 variable, then the leading term, when you look at it, is E2. And then if I were to differentiate with respect to E5, that's the upper separand, and it's just 3E2 E5 squared. Okay, that's it. There's nothing more complicated. It's just this. And then if I were to look at the smallest basis element there, well, you look at it and it's just E minus 2. Okay, and then the initial is just 1 and the separand is just 2 E minus 2. Okay. Okay, so it's just that. Okay? But remember, all of this depends on a fixed choice of an order, of a ranking on the basis elements. Okay. Okay, now this I think is the most technical slide in the talk. I think it's a bit hard to absorb the first time you see it. So I'm gonna try to explain it. I'm gonna try to explain this, okay? Okay, so using the above notions, this upper leader, lower leader, you can define a notion of reduction. You can define a notion of reduction. So I wanna define what does it mean I take two elements in my symmetric algebra, and I wanna say when is this, the first one, reduced with respect to the second one. Okay? Okay. So let's start with this slide. Okay, I take any little I given as a sequence, m1 comma dot 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 mn, okay, where the mi's are where the mi's, remember that the calligraphic m, right, it was the basis elements. The calligraphic n is the basis elements of the Lie algebra. And now the little plus simply means that these are the elements where in the grading are positively graded. You have a grading, and I have the basis, and then some of the elements in this basis are positively graded, some of them are negatively graded, some of them are 0 graded. Well, I take the positively graded. Okay. And now I define an operator. Di plus. What does this do? Well, I take an arbitrary m from my basis. Okay. And actually, the m can be arbitrary in the Lie algebra, but just take it in the basis. And what you do is you apply the Lie bracket. M Lie bracket with M1. And then that outcome, Lie bracket M2. That outcome, Lie bracket M3, and so on to Mn. And then, of course, this might not be a basis element, right? This is going to be some element in Lie algebra, but it might not be a basis element. Well, I take the upper leader of that. So now this operator gives me something, right, in my basis. If I did something in the basis, give me something in the basis. Okay. Now, given an element in the basis, L plus M is a set of elements, okay, in the basis which have the form Di plus M, okay, Di plus M is the one we just defined, with the additional property, which I have to say, it's an annoying property. I wish we could get rid of it, but you can't get rid of it. You can't. So you have to include it. That says that they have to have the property that whenever you have n less than m, then the same inequality happens when you apply the operator di plus, right? Okay, so these L plus M are all the applications of the di plus with this additional property. So think of this as I'm just applying the Lie bracket a bunch of times. Okay, if applying the Lie bracket doesn't give me a basis element, then I apply upper Lie there to get a basis element. Okay, and then I just want to look at those for which the preservation of inequality holds. This is this annoying sentence. This preservation of inequality holds. Okay. Anyway, I know it's technical, but it's really the natural way of doing this. Okay, and now we can define what do we mean by reducedness. Okay, and here's the definition. Okay, take two elements. Okay, in the symmetric algebra. Okay, we say that G is partially reduced with respect to F. Okay, if no element in this set, you have to look at L plus. Okay, L plus of big L plus, little L plus, and that should not appear in G. And then you do the same for the negative ones. You have to do for the pluses, and then you do for the minuses, and you have to check that no element in there. Sorry. And you have to do this for each for all the elements in the L's. No element in there appears in G. No elements in there appears in G. Okay. Now that's partially reduced. To say reduced, if in addition the upper leader of F, if it does appear the upper leader of F in G, it only does with a smaller degree than. Okay, I didn't define what the D plus was, but okay. There's a technicality here, so I didn't define the degree, the D plus F, but it's also natural reduction. Okay, it's also natural reduction. Okay, and now we can define for a sequence of elements in the symmetric, for a sequence of elements in the symmetric algebra. Okay, we're going to say that sequence of elements is partially reduced or reduced if every element is reduced with respect to the previous ones. Okay, so now you talk about reduced sequences. A reduced sequence is something that if I look at one entry in the sequence is reduced with respect to the previous ones. Okay, once you have developed the machinery up to now, it's the natural question to ask is, can I build an infinite, sorry, it seems like an emergency callback. Can I build an infinite, right, sequence, an infinite reduced sequence? Can I build an infinite reduced sequence? Okay, that's really the question. Okay. And if you give me an arbitrary Lie algebra, then you can do it. But in particular, there are algebras in which you don't, in which you cannot build an infinite one. Okay, and this is where the and this is an important notion that when you have a finite sequence. Sorry. Suppose that you have a finite reduced sequence, right? When you have a finite reduced sequence, then you can perform an elimination algorithm. Okay, then you can perform an elimination algorithm. Okay, and what does this say? It says that given any G, you can find another G which is reduced with respect to lambda. Okay, which is reduced with respect to lambda. So that's the outcome that you should take from this division algorithm. You start with whatever G. Well, I can produce a G1 which is reduced with the lambda you started with. Oh, sorry, the first bit is partially reduced, and the second bit is completely reduced. It's also a technical result. I don't think at this point, because of time, maybe it's not worth talking exactly about the details of this, but I think the takeout here is that given any G, I can produce a G1, which is reduced with respect to whatever reduced sequence you started with. Okay, so there is a division algorithm in this setup. Okay, and now the notion of Dicksonianity is precisely to say that every reduced sequence is finite. Okay, so the notion of the Lie algebra being Dicksonian says that every reduced sequence must be finite. Must be finite. Okay, so now here we're going to say that a sequence of distinct pairs, a sequence of pairs, is Dicksonian. Okay, so again, technical condition. But whenever you take mi and ni, then the mj's are not in the L negative of mi's, and the nj's are not in the plus of ni. And you don't want to have an infinite such sequence. Okay? This is a translation of the reduced sequence business from before, but it turns out to be just that there is no infinite reduced sequence. Okay? It seems like a strong condition, and I agree, but it is satisfied by plenty of Lie algebras. For example, the full bit algebra, the positive bit algebra, and the first Cartan algebra, they are all Dicksonian. They don't have infinite reduced sequences. Okay? And okay, here's the lemma that gives you Dicksonian. This is the equivalence that I was talking about before. And this is the division algorithm. If the Lie algebra is Dicksonian and you have a prime Poisson ideal, then the prime Poisson ideal can be written as a saturation of a finite set. This lambda is a finite set. As a consequence, the symmetric algebra has ACC on radical Poisson ideals. Okay? Okay. So now this is the main theorem. This was our main result, that the Dicksonianity assumption does give you the ACC on radical Poisson ideals. Okay, and I just want to finish now in the last minute saying that there are many classes of Lie algebras that are Dicksonians, as I already mentioned. The full bit algebra. And I mentioned the first Cartan algebra. It turns out that all Cartan algebras are Dicksonians. All the WNs are Dicksonians. Okay. And now I just want to point out that the bit algebra and the full Cartan and all the Cartan algebras are examples of simple graded Lie algebras of polynomial growth. So at the end, we were able to prove that if you give me a simple graded Lie algebra of polynomial growth over an algebraically closed field, then the same result holds. The symmetric algebra has ACC on radical Poisson ideals. And for this, we use a classification of such Lie algebras. Okay? And now recall that the expectation maybe is that the Dicksonianity condition maybe can be relaxed to linotherianity. And I think I'm gonna finish here. Yeah, I think this is my last slide. Thank you very much for your attention.
Yeah, thank you very much for your nice talk. Other questions? Well, I guess there are no questions. So thank you very much once again for your talk. And
yeah.
So,
yeah, thank you very much for the invitation again.
Thank you.
Thank you very much.
Bye-bye. See you next week.
Bye, everyone. Bye.